All right. Well, even with the help of the computational graph, it's a bit dull to continue deriving derivatives this way by hand all the time. And the fact that we can get this kind of systematic derivation of the derivative using computational graph might suggest that there's a way that we can automate this and just have the computer system maintain the graph and compute derivatives for us. And this is exactly what automatic differentiation does for us. If we have sort of in mathematical terms, we have some function y equals f of x, and then we could by hand differentiate that to get y prime equals f prime of x. And what we're going to do in automatic differentiation is we're going to write computer code that basically applies that function and produces the output, right? But the computer code will also sort of be able to, behind the scenes, keep track of other variables that it needs in order to compute the derivative of that function as well. And so given this function x, it will then be able to compute the derivative of that function for you automatically. And the way that it does this is simply by building up the computational graph you just saw. Again, that's a data structure for storing intermediate values and partial derivatives that you need to compute the gradients. And in particular, every node in that computational graph is going to represent some intermediate variable. It's going to store the value of that variable and the gradient or the derivative, partial derivative with respect to that variable, and the function that created the node, which is what you need to know how to do the derivative operation. And each edge in that graph, during the backwards pass, you're going to represent the partial derivative of, for instance, one variable u with respect to another variable v. And then finally, to get the overall gradient of the loss, or the partial derivative of the loss with respect to just one of those nodes, you find the unique path from L to V and multiply the edge weights, and here L is the overall loss. So that's sort of the basic idea behind how this can be automated on a computer. And the way to think about it is just that when you're performing operations with PyTorch tensors, it's not only calculating the output. What it's doing, in fact, is maybe not even calculating the output initially. It's just building up the computational graph so that it knows how everything's connected. And then that will all be held in memory. So all of those intermediate steps get held in memory usually. And then PyTorch can do the forward and backward pass through the graph for you in order to compute the gradients that you need. And it's a remarkable thing because it can happily go through functions and classes, and basically you just have to write the code that computes the loss of your network and then let AutoGrad and PyTorch do the rest. So why don't you now have a hand at computing the gradient of this function with respect to W and B the easy way, meaning with automatic differentiation.